So hi guys and welcome back. Today I would like to show you how we can work with the tree data structure in Rust to build like a suggestive search basically. So you could actually think of it as an autocomplete feature more or less. And if you remember, we already did some things in the past with the tree data structure in Rust. And now we are trying to use it to build an autocomplete feature. And so basically what this would do for us is that we'll try to use the prefix tree data structure, which is also of course an ordered tree data structure, to store like a dynamic set or associative arrays where the keys are usually strings. And they're not going to be like binary trees. They're not going to be like no nodes in the tree stores, and so what would do more or less would be like you can think of it as a tree with branches, and of course branches, and it keeps going down and down and down. So each branch has a branch and it goes from big to small. But in this case, of course, we're going to have like a base node, and then things are going to grow out again, just like you would in regular tree implementations or tree data structures more or less. So what I'll do is actually going to be pretty straightforward. I'm going to show you how we can use this to autocomplete characters, and also how we can use this to autocomplete words. So it's really going to be quite in depth, but I'm gonna make it as like as condensed as possible. And I've gone out here to actually set up the project. That's also what you can see here. So in here I have a bin, and inside here is going to be like one of my binaries basically. So I can also think of them as a library more or less. And this is actually the library that's going to contain our tree implementation. And then of course in our root projects, this is where I would bring this in to test it. Again, I'm setting this up with Tokyo, so just don't have to more or less, but I'm putting it here to basically easily have like an asynchronous time where I can basically just do whatever I want to do without any limitations. Of course, there are other ways I can do this, but I'm just choosing to do this with Tokyo. Okay, and then this is of course just coming from the library, which I just showed you. So we would basically making our implementations in here. So without further ado, let's jump right in and start making our implementation. So I'm going to focus more on the core logic, and so just to drive the point home, and then in the end, of course, there is a couple other ways we can do this basically, but this more or less can pass as one of those ways. So without further ado, I'm going to come down here and start making our implementation. The first thing I would like to do is to represent like a tree node. So would have like more or less you can think of this as a tree, and then with along this tree we're going to have tree nodes, and each of those nodes of course can now of course be recursive depending until we get to the end of the node. So I'm going to create a struct. I'm simply going to make it descriptive. So I'm going to just call it tree node, and it's going to have basically two attributes. So I'm going to have one called children, and I'm going to use hash map for simplicity. So it's going to have car. Again, like I told you, we're going to start with characters, so autocomplete for characters, like more or less what you could use for if you want to autocomplete words. So that when you start typing, for example, you want to write like London and it's at LON, then it should be able to complete the rest. So this is going to be word based. In the end, we're going to also do one that you can now have autocomplete for words, and then we can now use this for like to actually retrieve like a complete sentence. So in the end, we're gonna also have like a tree node. So this is going to be the recursive part, and I'm going to have a boolean here that's going to tell me if it's end of the word. So again, in the other case, it's going to be like if it's the end of sentence more or less. But anyways, I'm going to call this end of word just to make it as descriptive as simple as possible, and it's going to be a boolean. Okay, and that's basically all I'm going to have for our tree node. And for login sakes, I'm going to add the debug traits basically. So I'm going to just add debug. And now what I can do is down here, I would just add a simple implementation for our tree node that's going to help us to create a new node. So I need like a new function that should be able to return self. It should be able to return self, and what it's going to do again is it returns the tree node. The children is going to be simply say hash map dot common hash map is going on. hash map, the new. What is wrong with my editor today? And the boolean is gonna be, of course, gonna start with false. What's wrong with me today? I can't type. What is going on? Cargo FMT. Okay, so this is how I wanna have this looking. So this is going to help us, of course, create a new instance of our tree node. And now what I would like to implement is the actual tree itself. So again, I would like to export this. So I'm going to make this public and I'm going to call this tree. And again, I'm going to add this implementation up here. So again, we can be able to play around and see what we're doing, at least during the implementation phase. And this is going to have just one single attribute for now. I'm going to call this root. And the root is going to be, of course, of type tree node. And that's all I'm going to have for now. I'm trying as much as I can to keep this quite simple. So now I have my implementation for tree. Again, I would like to have a new method. I should also be able to export this. So I'm making this public. Again, it should be able to return error itself. And now I can do something like roots. And roots would be equal to tree node at new, basically. That's what I would like to do. Of course, I've done something that is quite crazy. So tree, and then I'm just gonna move this guy in here. So my bad. So like this, of course, this is how it should look like. And now for our node, I'm gonna add just a few implementations. So let's have an insert method. So I'm gonna pass a mutable reference to self and the word I would like to insert. So it's gonna be just gonna make it str, and I'm not handling errors for now. I'm just gonna focus on the implementation. Okay, so I would like to get the current node. So I'm gonna call this current node because I would like to get the current node where I would like to know where we are basically to decide, of course, what I would like to do going forward. Okay, so how I have a current node, and now what I would like to do is basically look through the characters that I have. So I can say call this ch, and say for ch in word dot cars. I'm going to look through the characters, and now what I can simply do is to basically try to insert. Again, that's what I try to do with this method. So I try to see if I can insert a new word, or more or less like basically if it exists, then of course I can insert, otherwise I should be able to create a new one. Again, I'm going to do this for all the characters of this new word. So I'm going to say current node. So for the current node, I'm going to look through the children, and what I can do now is look through the entries. So I'm going to pass, of course, the character itself. And now what I can simply do is maybe or insert. So if I try to get this and it doesn't work, if I'm not able to do this, of course, then what I should be able to do is to create a new one. So I can say tree node dot new. And now I should be able to have, I'm going to override this basically. So I say current node is this. And what I can now do, of course, is to basically, if this works in the end, I would like to update my current node and to the boolean to actually tell if this is the end of the word. So I can say current node dot is end of word, and I set this to true. And that's really all I would like to do. Is pretty straightforward. So again, we are now working with characters. That's also why we are looking through characters. Like I said, this is going to be as simple as possible. I like to have a function called search that's going to help us to more or less search like a character. So I'm not going to be modifying this. I just need the reference to self and then the word that we are going to be searching for. Again, it's going to be str. And now I would like to return a bool to actually tell me if it was found or not. So again, I'm going to get, like I did before, and try to get the current node. Again, this is going to be a reference to self.root. Now, something quite similar to what we did for insert, but now we would basically try to merge. So now I can say for character in word.cars, again looping through these characters. What I will try to do more or less would be maybe match to see if I'm actually able to get that character. So I can say, I can use the match keyword and now say current node, and I look through the children and I try to get the character itself. So I'm passing the current character where I am. So if I'm able to get this, if I actually have something, I'm going to call this node. This is going to be my current node to tell me where I am. I can say current node is equal to node. And if I'm not able to actually get anything, I can simply just return false. And now what I can simply do again is to update my current node and more or less, sorry, return the current, check for the current node and see if it is end of the word. And then if it is, then it of course means we couldn't find anything. And in this case, it's actually going to be false. So that's actually pretty straightforward. Now I would like to, maybe I can already, okay, I would like to implement a new method. So this is going to be like a delete. That's going to help us to be able to delete from our node. This is kind of the things some companies would actually expect you to do, like during an interview, which in my opinion really doesn't make any sense. But let's do this. So what I can actually do is to maybe write a helper function in here that's going to make it easier for me. It's going to be a local function. So I'm going to call this delete helper. The delete helper should be able to take a given node, and I'm going to be passing a mutable reference. So it should be able to take mutable reference of course to tree node. So I'm going to be able to pass in a immutable reference to a tree node, pass a word which I'm trying to, of course, delete. And I'm also going to provide a third argument that's going to tell me depth. This is going to help me to actually decide how deep, more or less, I would like to go, but also you would see that in a minute. So this function is going to be pretty straightforward. So the first thing I actually do is to check this depth. If this is equal to the word length, so if it is exactly the length of the word, then I can do a couple of checks. And one of them would be I would like to check if this is the end of word. So I can say node.is end of word. And if it is, I'm going to return false. And in this case, obviously, I'm not able to delete. And now, but if this goes through, now I can actually modify the end of the word. And now, of course, check if that node is actually empty. So the children basically are empty. So what I can do is node.end of word. I'm going to set this to false. And now what I can simply do is go through the children. So I can say node.children and I say it's empty. So it's going to tell me if it is empty or not. Okay, so now I have, so this is if this is the case. I don't want to return anything at this point. Okay, so, and now what I can actually do is now look at a given character, which is going to come from word, the characters of the word that was provided to be deleted. And then I look at the nth character, and this is going to, of course, be taken from my depth. Something is really not right with my editor. Unwrap. I'm not really actually handling I'm not really handling errors for now, so that's why I'm leaving this unwrapped here, because of course I employ you to do that. So now what I can actually do is try to now do the delete. So I'm gonna do some like node.children, and I need immutable copy of the character. So I'm gonna provide it like this. And what I can now actually do is to I'll try to of course do the deletion. So I'm gonna do, so if this goes through, yeah, I'm gonna call this child node. And this child node, I'm going to get it from, I'm going to do a little bit of a computation. So I would like to create a new argument here. It's going to be pretty long, like I'm writing Java. So I say should delete current node. So this is me trying to figure out if I should delete the current node. Again, now I can call the function. I'm going to call it recursively. So this is going to be child. Oh, something is wrong with my intelligence. Child nodes and child node rather, and now I would like to update the depth. And now I handle this if should delete node. If this is the case, if I'm able to do this, I'm just going to go ahead and remove it, of course. Children dot, I simply call the remove and pass the character as a reference. If this is the case, and now again I'm just going to return and say node dot children that is empty, which of course, as you can guess at this point, is going to be empty, obviously. Okay, so this is for when I have this. And again, I'm going to have a non-hand. And with this one, what I can simply do is to return false. Okay. And now in the end here, what I can simply do is, of course, if nothing actually works, I'm going to just go ahead and return false, basically. Okay, and now I'm just going to bring this down so we have more room to work. Or maybe I can actually just close it completely. And now, so with our helper implemented, what I can now actually do is to come here and call it, so I call delete helper. I pass a node, and our node is going to be a mutable reference to self. I pass the word, and for depth, I'm going to start with 0 basically. And we seem to have an error. Let me see. Oh, sorry, I need to pass the root. So not everything. So that's basically it. What we can now actually do is to go ahead to test this out to see what we have done so far. So I'm going to come over to our main file, and in here I'm going to create a function that's going to help me to test tree. So I'm just going to call it test tree. And then pretty straightforward. Let's create a new tree. So I'm going to create a mutable tree.tree. Sorry, I'm going to call this tree, of course. This is going to come from tree.tree. And I call the new helper function that we created. And now we have a reference to this. I'm gonna get back to you, Bruce. Okay, I'm gonna get back to you. I think this mostly happens when this language server actually crashes. But that's totally fine. So now what I can do is tree.insert. I'm gonna insert a bunch of things. I'm gonna maybe insert apples, and I'm gonna maybe, because I want to show you something. I'm gonna duplicate this several times. What happened? I didn't copy the right thing. So I'm going to change this to maybe something like ape E and then omit one. Or maybe I'll do it like this. And now the third one, I'm going to call this app. So just to show you how this actually diminishes. So it goes from app, apple, and then of course to the complete thing. And now what I would like to basically do here is to actually print this out. So I'm gonna print out I'm gonna maybe some like the tree, some like this. And Yeah, what I can, yes, I can simply just dump this in here. Okay, and I simply provide pass tree. And what I can actually now do is I come here and I can really now get rid of this. I'm gonna go back in here. Where is it? And get rid of it. I don't need this anymore. Okay, and now I come back in here and remove this. And now I can actually call this test tree like this and return nothing like this. So if you look at what we have so far, we have maybe I'm just come down here and try this out for you. So what we have so far is something like this, and somehow this singular word is going to cover everything we have so far. That's really the point. And I'm going to remove this because it doesn't really matter. It's not going to be able to duplicate this basically, but I can also remove it like this. And so if I expand this now, let me open the terminal one more time. And now I can say cargo run. I just want to show you. And now if you look in here, you see our tree. So the first thing in the tree is actually A. And then you see it's maybe I can also come in here. So you see what we have. So inside of this tree, um sorry, is this one? This is one of the nodes. So the first one, the children, it has children, of course. So the children actually goes all the way, because if you can see, this is in like an onion shell basically. So it starts first the roots and then the tree node. Of course, the root is coming from here, and then the tree node now starts from here. So the first one is children, then A, then inside of A we have P, inside of P we have another P until the whole apple is completely spelled out. So for you to get a sense of what is happening, this is actually coming from my language server for some weird reason. If I, for example, come in here and make another insertion and say something like, let me say, and I say mango, for example, you would see that we are going to get a completely new branch just taking care of the word mango. Okay, see, we still have A and then it goes P, P, L, E, spells that out and does all because it's an onion shell, this inside of this, then it goes all the way until it gets to this point after it's handled everything for apple and then it starts for mango. So what it also means now is if I come in here and add, let's say, a new word, something like this, and I say app, and I can say, I don't know, IJK, IJK, for example, you would see that it's not going to create a new branch for this, but it's going to branch out after P. So after P is going to go, one branch is going to go in the direction of L and then E, and then another branch is going to go in the direction of I, J, K. So that's really the point. So if you look here, it goes A, P, P, and then after P, now we get a new branch going in the direction of I, J, K. And then it stops here. When it gets to the end, it has to get to the end where the end word is false. And then it starts, as you can see that here, and then it starts a new branch again for L, and then it continues. Okay, so what it means again is if I come in here and insert a new word that says something like L, maybe L M O P, we'll see another branch after L. That's really what I'm trying to show you. So we'll see another branch after L. So again, we go APP. Then after L, one of the branches goes in the direction of E, as you can see, and the other one starts with M. Okay. Again, because you can see that here, because for E branch after APPLE, we also see that it's not the end word. So for this branch, the branch continues going in this direction. Okay, and that's one simple way we can actually just use this to like more or less do like a suggestive search, more or less like a an autocomplete feature, because now when we have this tree, and when you start typing, for example, app, we have the tree, we can traverse this tree, and then when we get to P, app, for example, once you type this out, we would be somewhere here. And then while we are here, we will now give you a lot of options. We can now give you something like APPLE, basically the whole thing. So we can give you APPLE, we can give you APP, of course, and we can also give you APPLMOP. That's really the point. So it keeps branching out in that order, basically. Okay, so what I can also quickly show you, maybe to drive it home further, would be try to using this to instead of characters, as you can see here, instead of characters, we're going to implement this for like a complete word. Again, it's going to be pretty straightforward, maybe a little bit more tedious in my opinion, but in the end, the concept is exactly the same. So I'm going to go back again to our lib file, and we'll start again. I think I didn't need this anymore, so I'm just gonna remove this. Okay, so now we can actually just implement a new tree for that's going to help us to search words, basically complete words, not just characters. So let's get to it. So it's going to be quite similar to what I have here. So I'm going to copy this just to show you that you can actually extend it to whatever it is you would want to do. So I'm just going to call this, maybe I'm going to call this compressed tree node. So it's going to be like this. So now, of course, it's going to be recursive. So here it's going to be itself and not like the regular tree that we had before. And again, just like we did here, I'm going to again copy this. Pretty straightforward. Just I'm repeating this so you actually can understand how this can come together. So I drop this in here. And so that's one way we can implement of course, our new method for our new struct. So now to get down to the implementation detail, again, it's going to be pretty straightforward like we did before. I might as well copy the whole thing, but I'm going to do it again just for you to really drive it home for you to understand how this should be working. So compressed tree node, I'm going to implement a bunch of methods. Again, we have a new method that's going to just return self. And in here, we simply, again, implement our struct. So the children rather, let me see. Oh, sorry, I'm going to do it like I did it before. So I'm going to call this compressed tree. So I'm going to copy this, bring this down here. And now we actually are left with just has roots. And again, I'm going to use a hash map, just like we did before. So you can simply say compressed tree node dot new, and we call the new method, and we are good. And what is the error? We seem to have some error. Yes, of course, I don't have this implemented. So again, I'm just going to come here, copy this. Don't copy too much code, otherwise you would get lost in the copies. And so this again is going to be compressed tree node, so that should be fine. And then let me format this again, cargo fmt, like this, looking good. Okay, and so now let's implement a bunch of methods again for this. It's going to be little bit more verbose in my opinion, but in the end, the concept is exactly the same. So I'm going to implement an insert method. It's going to be looking similar like what we had before. We're going to take a reference to self, and of course, it's going to take a word. And what we can actually do again is try to get the current node. So again, I get the current node like this. It's going to come from a mutable reference of root. And then once I have the current node, I'm going to try to check, maybe I can create another variable here. I'm going to call this remaining word. And this is going to be, I'm going to make it exactly as the word that we get. And now but this is also going to help me to actually check if Basically, it's going to tell me when to stop looping because now I'm going to write and fall a while loop basically. So what I would like to do is when this word is empty, so I'm going to say remaining word that is empty. So when until this is empty, so basically we would do this until this becomes empty. So that's why I said why this is not empty. So while it's not empty, we'll keep consuming it. So I'm going to create a boolean called found, and of course initially set this to false. And I would like to check or decide which keys to check. So I'm going to create another argument. I'm going to call this keys to check. Again, I'm going to look through my current node. So current node, and I'm going to look through the children, and I'm going to look through the keys. I'm going to clone it. So I'm going to call the cloned, and I'm going to collect this into a vector. So collect, and I'm going to provide some types. So this is going to be a vec of string, and yep, and is everything okay? Let me see. So sorry, should be like this, and what is the arrow? Cannot be built for magnitude development of car. Let me see. Expecting of a car. Let me go back to this. I think I made a mistake. Let me come back here. Of course, oh sorry, this should be a string because I'm working with a whole string this time around, not just a character. So that was also one good reason why it's not good to always copy code. But anyways, I want to format this and see what it's gonna look like. Okay, nice. Okay, so while I have my arguments, and what I can now do is go through my keys. So I can say for key in keys to check. What I can actually now do is to consider that argument we created before regarding remaining words. So I can say if remaining words starts with, and I'm going to pass this key, of course, by reference. Because this is one way for me to know whether to continue searching or not. So if it finds, then I would like to go in that direction of that node. So I can now say current node dot children. I would like to get this as a mute. I'll pass a key, and again, I'm not handling the error, so I'm simply just going to call unwrap like this. So now I have a current node, and now I'm going to update my remaining word. My remaining word is going to come from, of course, the one I have up there. So remaining word, and now I need just a chunk of it. So I say key dot length. Like this. And in the end, I'm going to update my mutable, my boolean update. So I can say found will now be true, and I basically break out of this loop because again for me it doesn't make sense anymore to continue searching. Again, I have to make this immutable for us to be able to do that down there. Okay, so now down here what I can now do is, if at this point we still haven't found what we are looking for, the word we are looking for, so what I can now do is to create a new key which is going to come from my remaining words. Again, remember it will not get here once we exhaust the string characters basically. And now I create a new node. It's going to come from my compressed tree node. What is going on? Compressed tree node, and I call the new method to get a new node. And of course I need to update this, so I can call my current node like this and update it with what I just created. So I can now say current node Let me see. I can say current node dot children to look through the children, and then insert. Now I like to, of course, insert on my key. I'm probably gonna clone it. Okay, this is not helpful. Clone, and now I'm gonna just pass the new node that we just created. And now what I can do is to update the current node. I can say current node is gonna be current node dot children, and I'll now get this particular one. So I'm gonna say maybe use get mute, and then pass the key again as a reference, and then not handle the error because I'm leaving that to you. And now at this point, I'm just gonna set our remaining words to empty string. So at this point, we would have consumed all our words. And now here, I would simply can update our current node to decide if it is the end of the word or not. So I can say if the end of the word would now be true. So what we are doing basically is to again treat our input as a word, not just a character like we did before. And then we collect the keys. Now these keys are actually the keys of our node. So that's also why you see it here as strings. So that's also why we are collecting as strings, because that's also, if I hover over this, for example, you remember that we are using the hash map here. The keys are strings. And that's also what we are considering to decide on which direction of the node we have to traverse to find the keyword we are looking for. Okay, so that would be our insert method. So the next one I would like to create is, I'm going to create a helper function. I'm going to call this search. So let me see. Okay, so this should also take a reference to self, because I'm not expecting it to modify anything at all. So I will not be taking immutable reference. So again, I'm going to get the current node. So let's mute current node. This is going to come from self.root. So I'll give us the current node, and again, remaining word. Remaining word will just be the word that we receive. Again, we'll do our for loop. So while this remaining word is not empty, so until it's empty, we'll continue looping. Again, I create a mutable boolean that we have to update, basically to help us know where we are in our search. So I'm going to call this found, just like we did before. And now I can do a for loop with key value pairs to look through our children. So I can create a for loop. The key, of course, would be key. The value would be a child node. So I'll say for this in current node dot children, and I'd like to iterate through this. And so what I would want to do here is to again check the remaining word. So if remaining word that starts with, because this is mostly all about string manipulation. So if it starts with the key, again, this tells us which direction to traverse in the node. So we would go in that direction once we find if it matches what we are looking for. So the current node now becomes the child node. That means we're going to traverse this in this direction. So now I say remaining word, because we want to exclude the words that we found. That way it doesn't take us back. We keep going forward. That's really the point. So if we start with APPLE and we found APP, or found a word started with APP, we continue in that direction, continue in traversing that node, so we don't go back to start APP anymore. We start exactly from where we are and just keep searching going forward. That's really what I'm doing here. It's not so fancy if you really think about it. So that's also why I'm chunking this like this. I say key dot length, and then I kind of like decide on the chunk of the word I want to proceed with. So I say found equal to true. So of course now I know, okay, I have to go in this direction in the node. So this should have been current node, not just current. So that's really what we can do here. And now again, we do our check. So if until this point, nothing is found, I'm just going to return false because nothing has been found. Okay, so but in the end, again, I need to update my current node to change end of the word. So I can simply just return this in this case. And of course, this should be returning a Boolean to tell us when we actually found something in our search. Okay, I'm going to create another function, helper function. I'm going to call this, actually, these functions don't need to be public. So I'm just going to say function also here. I don't know, let's see first. So I'm going to call this starts with. Again, I'm going to take a reference to self. I'm not really doing much here. So prefix is going to be a string again, just like we've been doing before. Because it's going to return a boolean if actually it fetches finds what we are looking for. So it's all of these functions are going to be similar. So I'm going to copy this. Now this becomes prefix. Okay, and now again I'm going to do something exactly like this. So this is going to be more or less like I would say a helper function, just like we had before. So I'm going to just maybe probably copy this part and then skim through it to see if that's exactly what I want it to be. So again, I have a Boolean to tell me when I actually found something. And now I again loop through my children as an iterator and then try to find the direction and then update the current node again, chunk. And if found, then I break and continue until that word is empty. And if I don't find anything, of course, this becomes false. So, but down here, what I can simply return is now true. Okay, so that's going to be like a really handy method, more or less, that's going to help us to like check if a certain tree actually starts with a certain prefix. That's like pretty straightforward. Okay, so now I would like to also maybe create a delete method. Let me see. I don't know if this is gonna be used, but let's see. Again, this should be public. So public. I'm basically adding this here just to help you for maybe reference sake, for example, because even though we don't use it, or if we end up not using it, at least you would have an idea how you could actually go ahead implementing yours. Okay, so I have a Boolean that's gonna tell me if something was actually deleted. And again, I'm gonna do something like something similar to what I did here. So I'm gonna have a helper function that's gonna help me do this. So I'm gonna have a helper function that's also similar to what we did before. The only difference now, this is not gonna be a tree node, it's gonna be a compressed tree node. Okay, and now word, of course, will still have, and of course depth. So that's more or less totally fine. So I'm gonna again do something quite similar to what I did. So maybe I can actually split my screen, come up here, and maybe copy some of this. So I'm gonna be copying a lot of code and then checking if they are doing exactly what I expect them to do. So first of all, again, I check the depth, if it is exactly the length of the word, and we are not yet at the end of the word. I'm going to return false. Otherwise, I update this and then return depending on the whether the word is empty or not. Okay, so that actually works. That's totally fine for me. And now what I can actually do is I can create an argument here called remaining word. And this is going to be, I'm going to take this again from the word and chunk this. So I'm going to say depth. I'm going to use depth. Okay. And now I can actually close this. I don't need this anymore, just so I can have enough space to work. Again, I'm going to create my arguments. Found. It's going to help me to decide if I found something or not. So found would be false in the beginning. And now again, key to remove. I need to know which key to remove. So this is going to be, I'm going to start it off with none. Of course, it's going to be an optional string, but let's see, it's going to be inferred in the end. Again, so let's do a for loop using a key and value. So a key, of course, is going to be a key, and the value is going to be like a given child node. So we say node dot children, and we need to iterate. I'm going to use immutable iterator. So when we loop through this, what I would like to do, of course, is again to see if the given word. So this is actually where we can maybe make use of this handy function we have up here. That's really the point of creating that function, but I'm gonna leave you to that more or less. So, but what I'm doing here is pretty straightforward. So if this starts with a given key, I'm always doing this because I need to know in which direction on the tree I should go. So once I find the direction, now I need to more or less decide which node I would like to delete. So again, I create a really long argument, a really long variable, and I called it should delete current node. And this is going to come from actually calling itself. So I'm going to call delete helper, and now I pass child node. Come on, child node. I pass the word, and I pass so in this case, what I can actually do is to pass the depth and the length of the key. The length of the key. And of course, I close this up. Go away. I don't need you. So, and I get if I should delete this, and I can say if should delete node. And what should I do? All I have to do, of course, is to now return this key. So I can say key to remove. I update this to this, of course, and I say key. I can simply just clone this. Come on, why does this keep happening? Key dot clone. And now I know which one to clone, and now I can say found would be true, and I break, of course, from the loop. And we seem to have a problem. Let me see. For loop evaluate unit type. Okay, this has to do, of course, with the return type. So I'm gonna leave this for now, of course, it's fine. So again, I check if we actually found what we are looking for. So if that's the case, I'm gonna return false. Okay. And now what I can do is now check the key to remove. So I can say I use the if let syntax and look through the key, and the key is gonna come from, of course, our key to remove. So if we actually have a key to remove, can now actually look through the children and remove that key. So I'm going to pass it by reference. And now I, of course, return, and this is going to depend on if the children now is empty. So I call this empty method and close this off. Otherwise, down here, the last thing for us to do is just return false to say, okay, nothing was actually found. And we still have okay, of course, we are still not calling this function because we simply have a function inside of this. So if you look down here, nothing is happening yet. So now we call the function now. And again, I pass a mutable reference to self. This is going to represent our node. And now I'll pass our word, and for depth, I'm going to pass 0. And sorry, I'm always passing self, and I need to pass the root. Okay, and that's really our delete method. It's also pretty straightforward and similar to the one we implemented before. Okay, so now what we can actually do is to, again, come over here, do some testing. So I can come here and say fn test compressed. I hope I'm writing that out pretty well. compressed tree. And we can also just call that up here as well. And I don't know why that you keep popping up. I don't know why you do that. But anyways, so now let's set this up again. So I'm gonna create a mutable argument called, I'm just gonna also call this tree, but this is gonna come from tree compressed tree, and I call the new method. And now, just like I did before, I'm gonna insert a bunch of things. So tree.insert. The word I would like to insert here is, again, I'm gonna say apple, and I'm gonna copy this a bunch of times. 1, 2, 3. Oh, let's see. So I have to close all of this up. And so now what I would like to do is, this is apples, and sorry, apple, and I can say apple and mango. Again, just to show you how this can stand in our tree. And now I can say apple and mango and orange. And then here I can say pine, apple, something like this. And again, just to keep it simple, what I can do is simply print the tree. So just for you again to see how this is stacked in the tree. So now I will go back to the terminal, so cargo run. And now you see down here, this is our compressed tree. And now you see, instead of working with characters, we are now working with complete words. And now if you look over here, we have this one that says pineapple. And then if we look at the end word, it should of course say true, because in this direction, there is nothing more. So after pineapple, that's the end for this. But after pineapple, we now have apples. So we now have apple. And then if we look at the children, we would see that we have some children, and it's not actually the end word is not false. So after within apple, the next word, of course, will not be and mangoes. Okay. And again, we have two ones. So it's going to, again, at this point, branch out in two directions. One direction is going to go in this direction. And so it's still going to be one direction because they are paths. So under this and mango, we now have two branches. So one would actually end here, and the other one will continue in this direction. Okay, so that's also what happens here. So one ends. So that's also why if we look for this complete compressed tree, which should be somewhere ending here, it says the end word is true. That's in one direction. In the other direction, it goes also and oranges, and then it also tells us here that the end word is true. So what it means now is, if I copy this, for example, and instead of and oranges, and I say and maybe banana, for example. And now you will see it's going to go apple and mango. So the roots in this direction is going to be apple. Then on the apple, we're going to have and mango. On the and mango, we're going to have two branches, one going and orange and the other going and banana. Okay, we are branching at mango. So you can also see here. So we have the next one as and mango. And then after that, we have and banana. And the last one would be, where is it? And orange, as you can see over here. So that's basically the point. So if we say something like this, let me see, it should also reflect down there basically. And that's also what you see. So apple and now and mango. So this is now a completely it is the another branch. Then on the and mango, we now have with banana going in a different direction, and then and orange going in a different direction. So that's really the point. So feel free to play around with these guys, and I will also write like a much more detailed article on this, because there are a lot of potentials, of course, of what you can do with this. I find this quite interesting because if when you take out or make out the time to actually play around with some of these data structures and really understand how they work, you will actually appreciate them, not just to scare, not just to maybe pass your coding interviews and stuff like that, but to really understand and actually apply this. Basically, using this, as you can see here, tree. Yeah, that's some data structure, but now we can actually use this to play around with some like autocomplete kind of like search. So anyway, guys, this is where I would draw the curtain. Again, like usual, feel free to reach out to me if you have questions. I'm always open to answer them. And yeah, um, reach out to me. Also, if you're new, of course, go ahead, subscribe. And yeah, until we see each other next time, have a lovely evening, guys, and stay learning. Bye bye.